This is the second part of our exploration of data types within C++. I'm really going to look at a couple of, I want to characterize them as miscellaneous things in terms of data type. We'll have a brief look at how we can cast from one data type to another. We'll also look at array-like structures and structs as well within it. So just sort of finishing off our brief exploration of primitive data within C++. We'll start off looking first of all at arrays. I'm not going to have a huge amount to say on this because it's something that will be quite familiar, I'm assuming, in terms of your existing programming knowledge. But, I mean, array, you know what an array is. So an ordered and bounded collection of data of a particular type. We can link it together. If you see a few examples here where we're creating an array of 5 ints or an array of 3 chars. And there's a little bit about how within C++ and C++11 you can actually initialize that array to give it a certain value, or to either set it to a default starting position or to specify the contents that it should provide. But if you want, you can pause this slide here and just read it by way of picking that up. What is important, or will be more important later on, is how multidimensional arrays are represented. And that's useful because quite often the data that we want to manipulate within our programs consists of two-dimensional arrays. One-dimensional, two-dimensional, probably the most common. You may have three-dimensional arrays or more so than that, depending on what it is you're writing. But you can see here, the box on the left-hand side, we're creating a 2x3 array of ints, so a total of 6 altogether. And on line 3, we're initializing that to the values 1, 2, 3, 4, 5, 6. And you can see in terms of how we've initialized them using our braces, we've clearly differentiated and delimited, well, what's in the first row and what's going to be in the second row of data. Line 6 is exactly the same. So there again, we initialize the data in the same order, 1, 2, 3, 4, 5, 6. You can see in this case, we've just removed the inner braces, so it's sort of assumed then, and we're using line spacing here to make clear content of each row. And line 9 at the bottom, we're doing exactly the same, just in terms of 1, 2, 3, 4, 5, 6. And this gets at the fundamental essence about if we create an array, even if it is multidimensional, it's going to be stored as a single block of contiguous memory on the actual device we're running on. And that's important because when we're looking at how we step through an array, be it single or multidimensional, we'll want to jump from one location to another location. We want to be able to calculate whereabouts we'll find a certain piece of data within that array. And we'll have a look in a few lectures' time at how we can calculate positions and jump about between arrays. And key to that is the underlying assumption that when we create an array, it is a block, continuous block of memory that we've defined out. And we know the size of each of the elements or the size of each of the rows, then we can jump amongst that particular chunk of data. Casting then is the next area. There's a few more things we want to say on this. Casting in C++, it's a mixed bag. There's a number of quite nice elements, and there's also a number of truly horrendous elements. We'll start off looking at how we can cast data, specifically in C++11. And the next slide, we'll look at the older forms of it as well. C++11 actually introduced 4 different ways of casting data. So converting data from one type into another type. So you notionally maintain the same value in whatever sense that is, but you're converting it from data type A to data type B. C++11, we have 4 casts available. You can see them: a static cast, a const cast, a dynamic cast, and a reinterpret cast. Now, 2 of those are lovely, and they make a very nice distinction that is always useful for us as programmers to have. And any time we're converting or casting data, to keep in the back of our mind what type of cast do we want to be using. They are static and they are dynamic. Now, C++ is one of the few languages I'm certainly aware of that makes a clear differentiation between the two. In other languages, your Javas and so on, it isn't necessarily as clear as to if it's done statically or if it's done dynamically. A static cast is something that is done at compile time. Dynamic cast is something that is done at run time. And we will be looking at all of those in a lot more detail whenever we get on to classes. The other two, the const cast and the reinterpret cast, they're not good things. They're things that ideally you should never ever have to use, and you should never feel comfortable using either of those types of casts. But we'll look at those when we get on to objects. Two I want to look at, well, the one I specifically want to look at here is static cast. It's applicable in most ordinary situations, certainly if you're using primitive data. Accepts a data value and returns the equivalent data type of the specified type. So you can see an example here at line 1 in their little fragment of code. We have two ints, n's 2 and m is 4. On line 2, we're creating a double value called ans, and we want to set that equal to n divided by m. Now, if we're using integer arithmetic, integer 2 divided by integer 4 is going to be 0, but we want to have an accurate floating point representation. So we're going to convert the m into a double. So we're seeing here the use of the static cast. Inside our angle brackets, we're saying we want to convert m, which is an int, into a double, and that'll take the 4 and convert it into the double value 4.0. We then get to divide that. Now, n is going to be an integer, and that static cast is going to give us a double. So we can't divide an integer by a double, so we'll have an automatic, at this point, conversion of the n integer into an equivalent double. There we'll have one double divided by another double. We can do that, we'll get the answer, and we'll store that within the ans value itself. So it's normal casting. To be honest, it looks a bit cumbersome having to stick in that large static cast in terms of not being particularly elegant, if you might be comparing it against, say, Java or your existing knowledge of it. And you'd be right about that. But we will look at casting in a lot more detail when we do get on to objects in terms of what the other types are used for. The old style casts, which are still available in C++11, if you're using C++98, this is the only ones you have accessible to you, look more or less exactly the same as the form of casting that's used within Java and C#. So it's going to be more familiar. So you can see the example over here is n2 and m4, where you're looking at a double answer is n divided by, inside rounded brackets, double m, or to convert double the m in the second line, line 3. So that's a more familiar way of doing the casting, and that's what C++ supported for many, many years. I'm going to answer a question about the warning at the bottom about, well, why in C++11 did they feel they had to move away from what is a perfectly nice and common way of casting from one to the other. But before I do that, just to mention, second paragraph, C++ can also perform automatic typecasting. So that's where, for example, both on line 2 and line 3, we have an int divided by a double after we've done our explicit cast. Now we can't do that, so an automatic cast is where they take the n int and behind the scenes turn it into a double. So we can divide one double by another double and get our answer. Now, the reason why in C++11 they moved away from this form of casting and introduced the 4 other ones, even though it looks a bit more ugly, is that in traditional C++98, if you cast from one type to another, it does it, no questions asked. So if you say, I want to take this and convert it into something else, it will do it. It will try its best to do it, even if it doesn't make sense to do it, even if it's likely to be very dangerous to do it. C++, as you remember, was created in a time where you didn't really want to be spending CPU cycles double checking if things were okay. If the programmer told you to do X, then he or she, you assumed, was right, and you did whatever they wanted you to do. Not always a good thing. The example down at the very bottom highlights this. So at line 1, we're creating a pointer. So it's going to point to a bit of memory, and it's a pointer that points to a double. In this case, it points to an array of doubles. So this is a pointer, index into a piece of memory, and it says that the memory that I'm pointing to should be interpreted as effectively doubles. That's how you interpret the bytes, the 1s and the 0 at that location. In line 2, we're doing something incredibly dangerous. We're saying I want to take what is a pointer to double data, and I want to consider it as if it's a pointer to characters, to chars. Which means that if I manipulate that data, I am messing up doubles. I can't interpret that. How you fundamentally interpret your 1s and 0s between a double and a char is completely different. So in doing this here, what I have there will not be chars to begin with, it'll be doubles. Whatever I change, I can convert it back into double value, but what that double value is going to be somewhat meaningless. So line 2, C++, if you wrote this, will say, yep, sure, fine, no problem, I'll do it. Won't generate any warnings or things like that. Any good compiler maybe, but I'll let you do it. Line 3, if you use the static cast, it won't do it in C++11. It will say, okay, I've got a pointer to a double. You want me to convert this into a pointer to a character. I don't know how I can safely do this. And we're going to come back to static cast later on and look at some of the rules around casting, and particularly in terms of user-defined data. In C++11, if you try to do a cast, the compiler is going to work out how it can safely do that cast. Does it know how it can chain these things together? And if it doesn't have any way of doing it, it'll flag it up as something it's not capable of doing. So it does look more cumbersome. Line 3, much more safer. So it's certainly the thing we would want to use. So let's give you an example of where in C++ we need to be slightly careful. And this is going to tie into the fact that integers can be booleans. We think back to our numerical int type data. We had ints, we had chars, we had characters, we had booleans, bool values. They were all types of numerical data. We need to be careful if we're using that. So let's have an example. I'm going to show you a fragment of code, and I want you to work out the conditions under which the if statement will trigger, will be true. And what I'm telling you at the top is C++, it's an integer to be used as a Boolean value and a Boolean to be used as an integer. They're all types of numerical data from the viewpoint of C++. Can lead to some unobvious outcomes, depends on your perspective, how you see things. So we've got an example here. Now I want to trigger an action if counter, which is an int, is less than some other int or target. So in this case here, we've got count 2, we've got total is 4, and I want to, if my count is less than my total, then I want to do something. I want to trigger some action. So I've said here, it's the other way around. If count is greater than or equal to or total, then I want to trigger some actions. That's what I have down in my if. So if it's not the case that count is greater than total, then I'm going to trigger it. So I'm going to come to this here, check if count is greater than total, true or false, and depending on that I'll negate it and I'll then trigger the action based on that. So in this case here, I want you to spend just a few minutes to ponder under what conditions will that be true? Under what conditions am I going to have a count and a total value that will enable that particular trigger to happen? Okay, so you can sort of pause it here, you can have a bit of a ponder, and whenever you're happy, you go on to the next slide and you'll have a look to see what actually happens when we execute this. So in terms of executing this fragment of code, we have to look at the operators that are applied to it, and we have two of them here. We have a negation and we have a comparison, a greater than symbol. So similar with plus and multiply, if we've got a sequence of operations together, we've got to work out which one do we do first of all. Do we do the addition or the multiplication? And this is where all languages define a sort of list of precedence for the operators. Which operators have a higher precedence than another one? You do those first, and so on all the way down. Negation actually has quite a high precedence. So that's, and this greater than comparison is quite a low precedence. So in terms of which one do we pick, we go with the negation first of all. So in terms of how do we interpret not 2 is greater than 4, And line 2 shows us the correct according to the language way of interpreting it. We do not 2. And then after that we say, is that greater than 4? Now, not 2, we've a small problem with this, because how do we do that? Not 2 doesn't really make sense. The notion of negation applies to Boolean variables, to true and false. A true becomes a false, false becomes a true. That's negation. So what C++ does here, it says it has a negation operator. It needs a Boolean value, but I've got a 2. But I'm allowed, because a bool is a piece of numerical data, I'm allowed to convert a number into a Boolean. And that's what it does. It says, okay, number 2, what Boolean value does that correspond to? And as we know, I've already said this here, that if 0 is false, anything else is true. So a 2 gets turned into a Boolean value of true. And then we have not true, that we can evaluate, and we evaluate that to false. So we end up then with a statement that false is greater than 4. Okay, we can't really do that, because the comparison really needs 2 numerical values, not a Boolean value of false and a 4. But we can take a Boolean value and we can convert it into an integer. We know that. So if it's false, it's 0. If it's anything else, true or false, it'll get turned into a 1 in that particular case. So false gets turned into 0, true gets turned into 1. So in this case, we can do this particular conversion. We'll do this here. False gets turned into 0. 0 is greater than 4. We can evaluate that, and it evaluates the false overall. So in this particular case, the not 2 greater than 4 has a final evaluation of false at the end. So it's not actually going to trigger. So in terms of actually triggering this here, we'll need a total value is actually going to be 0 or less, and then whatever values are true or false it will have for doing that. So it's not necessarily intuitive or obvious, but it's simply because of the implicit type conversion and the fact that C++ will quite happily convert from a bool into an integer value and vice versa. And exactly the same argument question applies to a char value as well. We can cast them into numbers one way or the other. So other things to look at, one's about data size variation. We briefly talked about this on the last lecture. So we mentioned here that a long's not that long. So an int and a long are both mostly 32 bits, 4 bytes in size in most platforms at the minute. C#, Java, a long is an 8-bit, 64-bit, 8-byte, 64-bit value. And this is the thing about C++, there's no guarantee of what size it is. That's where your C limits file comes in. Language specification just simply requires that a long is no smaller than an int, so it can be the same size as an int. If you don't like that, Visual Studio actually has a number of sort of headers where you can use built-in types to say you want to have a 16-bit or a 32-bit or a 64-bit signed or unsigned integer. And sometimes you'll see that being used just by way of being explicit. Structures then, so it's just miscellaneous things we're going through. We'll mention briefly here about the use of structures. We're going to look at this more whenever we get on to object types. So for primitive data, if we want, we can package it together into sort of coherent structures, structs. Nothing more than packaging them up. And you see a couple of examples here where we have a struct called struct type. Inside the braces, we're declaring the data that we want to piece together to form that particular struct. It can be primitive, it can be object-based data, it doesn't matter. And the example at the top at line 6, we're actually declaring a couple of instances of that struct. And the example at the bottom, we're not, but we're still including our semicolon just by way of the language definition. And you can see, given a struct, we can use the dot operator to access one of the members within that particular structure. So they're useful quite a lot of times when we want to group data together, but not to the full extent of saying we want to create a class where we're being more explicit about the data groupings that coherently fit together and the operations that apply to those data groupings. A little bit of this here, again, you can pause and read it if you want to, about how you can initialize the data within the struct. There's sort of usual rules you might expect about doing this, or if you don't have enough data to populate the whole thing, in what order are the values initialized. Overall takeaway, so I mean, we spent this in the last lecture basically looking at data in C++. It's high level stuff because a lot of this you'll be familiar with. The interesting things about C++ is a little bit more low level. It says that, you know, fundamentally your numerical data, your integers, your chars, your Unicode, or your ASCII values, or your booleans, ones and zeros, they're all going to be represented as ones and zeros in the end. So C++ doesn't hide the fact about their underlying representation, and is quite happy to let you convert from one into the other, which can be useful in some cases, can also be problematic in other cases. So we need to be careful about that. Useful in terms of learning C++, just to have a good understanding of those core fundamental data types. There's a lot of rules, legacy things about C++, rules and regulations about how things are initialized and things like that. You want to pick them up, useful enough. From my point of view, I think it's good enough just to know the core subset of them and understand some of those fundamental premises about how that data is represented. That's the key thing to take away. Ultimately, for languages like Java, C# and other ones, data will be represented in terms of ones and zeros. So have a think about how they, as languages, treat this exact same process and the rules that they put in place to try to, from a programmer's point of view, to make it clear, to make it explicit about how primitive data can be defined and how it can be manipulated.